also, like the time taken for processing, because it's a simpler framework. So that's what we did. We improved the time and we almost got the same rate of error, even though the Kalman filter is more complicated than the surface approach. So this is just the brief introduction of our paper. Yeah, just the introduction. I would not want to waste more time on this. Yeah, so what I wanted to show here is what SLAM is. SLAM is just nothing but simultaneous localization and mapping. Localization is accurately determining a robot or any object's correct pose, angle, when it's going in a straight line. So that's what localization is. So what autonomous cars do is employ SLAM. It accurately determines the position, velocity of the particle, and it maps its entire surrounding so that it can accurately determine where to go and where not to go. And there are so many algorithms like LIO-SAM, FAST LIO-SAM, FAST LIO-SAM, FAST LIO2. So all that are there. What we've done is we just took FAST LIO2 and we made it better. This is why we use FAST LIO2. It's lightweight and what we built upon. This is the base algorithm. It's just, this algorithm is lightweight and efficient, and IMU is nothing but an inertial measurement unit. It measures the angle. There's a tool called a gyroscope. So gyroscope accurately gives the angle of tilt, angle of direction, what angle is moving at. That's what IMU data is. What it does is it uses IMU data and LiDAR data directly. So it doesn't process it as much, which makes it better for accurate real-time mapping. And point cloud feature mapping. Point cloud is nothing but when there's a LiDAR, it generates accurate points of the surroundings and it combines all the points along with IMU data to generate the proper map. That's how all SLAM algorithms basically work. FAST LIO2 is just an improved version of something called a LIO-SAM. And what we're doing is we're making FAST LIO2 also better by introducing surface. Now I'll just move on to the next one. This is just too much theory. Yes, this is methodology and design. This is the base FAST LIO2 algorithm which we took. It just takes raw IMU data, and what IMU data is, it gives initial velocity, it gives position, it gives orientation estimate, like how much it's tilting in x-axis, y-axis, z-axis, and then it takes LiDAR feature extraction. So we just use a LiDAR sensor, it just emits light, it reflects, comes back, and it records wherever it touched as a point in space. That's what a LiDAR sensor does. And it does something called a state update, uses iterative closest point and point to plane constraints for fast alignment. Like, yeah, that's there. And then it outputs a drift minimize post. Yes, it's something called Kalman filter. I would not want to go too deep in it because it's a very vast topic. Let's just call it a filter. It's just a linear filter which takes some variables and it's used for state estimation. Like it's used for predicting what the next position and velocity of the object will be at a further instant of time. That's what a Kalman filter basically does. And it uses an iterative approach. That's why it's called an iterative extended Kalman filter. But the problem with that is it is very highly computational. It has many layers to it. So what we have done is we just removed that totally and added our own thing called surface. It's not our own thing what we developed. It was already there existing, but we have integrated it with this algorithm to make it better. This is not required. It's just an IKD-3 implementation. I just added all the theories so that I could show, and if any questions were asked, I could go back to the slide and you could ask me questions. Okay, so this is what I was talking about. What we use surface for is it replaces the iterative extended Kalman filter, which traditionally handles SE3 pose transformations in conventional approaches. And challenges with EKF, it suffers from computational inefficiency, high dimensional transformations, and it has numerical instability. When the car moves too fast and it accelerates too fast, when it's going through a tunnel, the Kalman filters cannot process so much data at once because it needs to do the same thing again and again and again, and obviously you need a very fast processor for it, and you need a lot of computation that generates heat, that generates errors, because no sensor data will be absolutely perfect. That's one reason it's highly accurate. I'm not denying that, but the thing is it's not as efficient as surface because it just uses small matrix transformations to get the next predicted position. It also predicts the next position, but it uses matrix transformations. It is not a filter like IEKF. Yes, ma'am. This last point is an important impact on system performance. It reduces the computational complexity. It uses something called Lie algebra, and it enhances the stability. It reduces transformation errors and improves real-time data. So this is the basic methodology and design. So what we do is we start and you initialize a system. Then you initialize the system as in you turn on the sensors, you turn on the LiDAR, you turn on the IMU, and then you go to data acquisition. You use the LiDAR to generate the point clouds, and you use the IMU also to gather all the data. After that, you pre-process it. You do not do much of pre-processing. The main thing you do is, if anything is in the LiDAR point cloud, if it is too far out, like if there's no neighboring points, you just discards it because it will be called an outlier. And then the next step is the surface filter application. After the surface filter, again it transforms it. What it does is, it takes the IMU data, it takes the LiDAR data, it combines them. You need to do sensor fusion to get the accurate position of a system in space. And then it updates the map. After that, if you test and evaluate, we have shown the test and evaluate results, and we've compared both of them and shown how surface is better than the IEKF method. Yes, that's what I've said. Yes, sir, even this. That's just whatever I've explained. This is mostly the same. This is also multi-sensor data fusion. LiDAR and IMU data are fused in a common local frame to achieve better noise handling, because combining IMU and LiDAR helps reduce the effects of sensor noise and drift. Also, the key components are LiDAR odometry, it gives a high frequency pose estimation. IMU pre-integration and refines pose estimation between LiDAR scans, because you cannot completely rely only on LiDAR. You can obviously use only LEO SAM, that's a thing that uses only the LiDAR. But then if you integrate this thing also, IMU also, you can get the accurate angle of the position of the object. Yes, so this is the data set we've used. This is our own college RVC. So what this does is, we don't need the camera data, we're not using camera data, but we just have it for another algorithm. We use the same thing, that is how the LiDAR map looks. So we've used this to generate some results. Yes, that's our campus. That's the lab we actually work in. So we just took a full round, and then this is the LiDAR data. You can see here, that's the 3D LiDAR scan. Like it's emitting the light, and it's hitting a point. When it hits a point, what it does is, it reflects back and it marks that it's hit that point. It's a 3D LiDAR, it's not a 2D LiDAR. Yes. This is a ROS Viz. It's a ROS based software. ROS visualizer is ROS Viz. Just start a terminal, type the ROS back play, and then just type RViz, it will visualize. Like it comes inbuilt with ROS, robot operating system. Like how the previous presenter told Gazebo, right? This is also software for visualization. No, so it's there for everyone. Like we've used it for our project. Also, we have not used the camera. We just kept it there because it's useful for other algorithms. This is just one algorithm. There are multiple algorithms for the same. There's something called OS-SLAM, ES-SLAM, all that. Yeah, so this is how, that is called RPE, which is a relative pose error. That is what we have improved as FAST LIO. This is RPE of FAST LIO 2. Relative pose error, and that is absolute pose error. So as you can see, both of them are almost the same, which is quite a good thing, because even though we have reduced the complexity of the filter, Kalman filter, we've got such a nice result, because you cannot see much of a difference. Yes, that is a little thicker than this, which means there are more data points, but again, that has a more computational load, so obviously it will produce that. And then here also you can see these both are the same almost. And these are some numbers also, it's actually calculated by us. Yes, so AP, RP, same for both. We have the max, median, mean, min, RMSE, root mean square error, and sum of square errors and standard deviation. It's nice to know that the AP of FAST LIO 2 is more than FAST LIO 2, which shows that, and also the standard deviation of this is more than this, which means that FAST LIO 2 actually has variability in what data it gives. It's not that much, I agree, but it is more variable in this, which makes this a better choice. Also, one more thing to see is that the median are same. The max is almost the same. All the parameters are almost the same, which is what we want. Because that uses less power first of all. You don't even need that big of a processor. You can even run it on small ARM boards, like RISC-V boards. Negligible difference in accuracy. Both algorithms demonstrate almost identical performance across all metrics, and as FAST LIO 2 is preferred. Yes, this is also one more important metric. It's seen that FAST LIO 2 achieves an absolute pose error of 1.0578 and relative pose error of 0.24%, slightly surpassing it. If it's more, means there's more error, which is fine. Because first of all, we're not using that complicated of a filter in Surface. But even then, we are getting such a close result. Also, but one very good thing to note from this experiment is that as FAST LIO 2 outperforms FAST LIO 2 on average processing time. There's almost a 10% decrease in the time, which is very good. Milliseconds may seem very less, but in real time, that's a lot. So this shows that it's very scalable also. It can run on low power, and it's a very easy implementation of the same algorithm. These are the references we used. Yes, ma'am, the FAST LIO 2 uses Canon filter. Yeah, the FAST LIO 2 was the one like in this. So basically, this is generated using the Canon filter. And this one is used, doesn't use a Canon filter, this uses Surface. That's why it's called S FAST, Surface plus FAST LIO. This, what we've done is remove the Canon filter. Here is with the Canon filter. Yes, that one. It's there. Yes, this is the FAST LIO algorithm. And so it takes raw IMU data, which is the initial velocity, position, orientation, and then it takes the LiDAR feature extracting the sharp edges, planar surfaces. For example, if it were to hit this table, it accurately determines that is a sharp edge, like that. And then it performs a feature matching to locate the vehicle. And then it uses status update, which uses iterative closest point and point to plane constraints for fast alignment. And it outputs a drift minimized post. Pose is nothing but, if there's something called a pose graph in robotics. So whenever a robot moves, ma'am, some of it is heavily mathematical. Like the Canon filter is, yeah, that is very mathematical. That's why we didn't try to put it here, because surface, ma'am. That's also mathematical. I could explain it to you in words, because if we put it would fill like 100 slides, like a lot of complex mathematics. Like the Canon filter is just a linear filter. So it's basically just used for prediction. Like you have current velocity, what is the future velocity? Both of them do the same thing. Current velocity I have, how will I predict the future velocity? Canon filter uses a linear filter approach. So if it predicts a velocity, then it calculates the error, feeds the error again, and calculates like a feedback loop. That's how Canon filters work. But Surface, it doesn't do that. It uses matrices, like rotation matrices. Something called SC3 was there. So SC3 basically means it's rotating it it's a third degree equation, and it's rotating it in the third degree. That's what it means. And if I were to explain the mathematics, I am not a pro myself, unfortunately. Also, that's like a little too deep to give in a PPT for this one. That's the only reason. The future scope would be to try the same surface with other algorithms, something called LVI sample. So in that also it uses Canon filter. We can try implementing that, because that uses visual data as well, sir. Like it uses the photo data, like it takes the video. So it uses that. Instead of Canon filter, we can put surface and see how that performs. This to optimize whatever is existing. This is all the FAST LIO 2, FAST LIO 2, LIO SAM, LBS SAM, everything we've implemented. This FAST LIO 2, we just got the results to see. Yes. rather. Any other inputs from your side? Right. It's actually a joint effort, sir. My partner and one more partner, and then there's 2 more people there. It was like a complete, it's not a leap. Yes. Yeah, they keep working on projects. So from big autonomous car, there's one more small one which is take to competitions. So you can try. Yes. In fact, one thing we did was we tried using another small algorithm called Hector Slam. It's a 2D lidar we used. We mapped the floor using a small car, autonomous car, very small car. But we didn't use such complicated things because the competition requires a lot. We did not have that particular board access at that time, so we could not use it. Like for this, we used our PC. This runs on an Intel i7, that's I think 12 Gen. So that will do it fast. But then if this is a small board, it cannot perform this stuff. That's why Surface you have to try. Like the small board cannot perform as fast LIO. By that time we did not have access.